I'm going to cover a lot of material. Please do take notes. I've offered to Patrick and Elena that they can distribute a PDF of this presentation, which includes some of the useful links that you'll find there. And at the end, I have a set of contact information if you want to follow up with me on any of the material or follow me on LinkedIn to stay in touch. That would be great. Okay, so let's talk about NoSQL and SQL DBMSs. What works for big data? And this is going to be a survey. We're going to look at the whole set of database management system technology and try to sort it out in 40 minutes or less. Our purpose is to equip you to be able to go into an industrial situation, a business situation, and figure out what the best database management system will be for the application and the data that you need to be processing and running analytics on and providing value to the business for. And hopefully at the end of this presentation, you'll be able to go out equipped with some knowledge, some resources, and be prepared to do that work. And Patrick, I noticed at least one person is not hearing the presentation. Chad Dupresne. Maybe
I will deal with this. Don't worry.
Okay, all right.
Okay.
I'll take care of it.
Okay. Thank you. So I will continue on. So here's our agenda. First of all, we're going to talk about what big data is and why it matters. Then we're going to talk about database management systems in general. Then we're going to step through the four major types of DBMS, and then the fifth, which is hybrid, which spans the other four. So first of all, what is big data and why does it matter? And I have to start by making sure that everybody is aware that big data is first and foremost a buzzword that's used by vendors and consultants to draw in business. There's still great debate as to whether or not the term means something. I do believe it does mean something, but it's been so abused, it loses some of its meaning. So what we're going to do is get past the buzz to the substance. And what I think big data really is an observation that data volumes are so large anymore that we can't just continue to use our traditional SQL DBMS tools in order to process the modern form of big data. We have to do something different. So that's really, I think, the significance of the term big data. It's usually defined in terms of 3 V's. There are some variations on this, but these are the basics. Volume is the first V, and we're talking about hundreds of terabytes to petabytes. So let's try to visualize that. A terabyte is 1,000 gigabytes, which works out to be 1 trillion bytes. And that's hard to picture, but think of it this way. A 4 gigabyte flash drive is pretty standard these days. You can actually get flash drives that are larger than that. But if you put a pile of 250 4 gigabyte drives, USB flash drives, piled them up on a table, you'd have a terabyte. You'd have 1 trillion bytes of data. So that's a good way to visualize what a terabyte is. Now, we really don't consider a terabyte of data big data anymore these days. You have to be at least, 50, 60 terabytes before we're going to say, well, that's big data. Things have gotten really big. The next triple power of 10 is a petabyte, which is 1,000 terabytes, which is 1 quadrillion bytes, a number that's really hard to envision. So for a terabyte, you had to envision 250 of these little 4 gigabyte flash drives. Now you have to envision 250,000. You're not even going to be able to pile those on one desktop. That's going to fill a lot of disk drives in a data center somewhere. So when we say big data, the first V that we're talking about is volume of data, usually about 100 terabytes or more, up to sometimes several petabytes, several quadrillion bytes of data. It's a lot of data. So the next V in big data is variety. What this is really saying is the data doesn't all come in a regular schema that repeats over and over like a big table or a set of big tables. It's often unstructured data, human-readable text, coming in a great variety of forms. That's something else that makes big data challenging because our traditional systems could not deal with variety. They could only deal with fixed or regular schemas, regularly repeating data. The third V is velocity, and that means data that's changing frequently or coming to us fast. If you think about all of the units, all the electronic devices now that have sensors in them that can constantly monitor and relay back to some collection point their GPS location, their temperature, their acceleration, what Wi-Fi networks they're finding or Bluetooth networks, it's a tremendous amount of data that flows in very quickly. Also, many companies, many retailers, companies like Facebook are tracking how people navigate through their sites. And if you're a Facebook with hundreds of millions of users and you're logging every one of their mouse clicks, again, just a very rapid stream of data coming in. So with big data, with huge volumes, a great variety, and a high velocity of incoming data, we can't just stick to our traditional tools. We need new tools. Now, why does it matter? Because internet scales matter. The 21st century is pretty much defined, at least so far, by companies like Facebook and Amazon that are working at global scales that were just unimagined before the World Wide Web took over. So it really matters. And our culture, our lives, our livelihood, our businesses depend on big data. And as already mentioned, the Internet and the Internet of Things are generating more data than ever before. We need to know how to process and handle this data. It is now ordinary for an application to process hundreds of terabytes in real time and or offline for analytical applications. As professionals, we need to know how to do this. That's why we're here tonight. Now, it's fun and a little scary to dive into big data, so I want to encourage you to resist the hype and resist the buzz. Don't fall in love with just one DBS that might be wonderful, that might do all sorts of things that traditional tools could not do, and that might all be true, but remember that every DBMS style, whether it's tabular or columnar or key value or graph or document or whatever, they all have their advantages and disadvantages. They're better suited for some applications, worse for others. Every combination of a product and a vendor has its advantages and disadvantages. We're limited by physics. We're limited by human capabilities. Nothing's perfect. Keep in mind that there are some really traditional and tried and true products that have been dealing with big data, tens or hundreds of terabytes, for years. It's not all new. The buzzword big data is new, but the reality is there have been a few platforms doing big data for years. So learn to judge between them. Learn that we're not going to pick the world's best database because there is no such thing. We're going to pick the best database for our application as far as we can tell. And be skeptical of vendor claims. Be skeptical of benchmarks. One NoSQL DBMS vendor said, you've heard the phrase coined by Mark Twain, there are lies, damn lies, and statistics. And he said, well, now we have to modify that. There are lies, damn lies, statistics, and vendor benchmarks. And this was a vendor telling you this. You have to be careful. So be an aware buyer. Resist the hype, resist the buzz, make a judgment as a professional as to what's best for your application. Now, unfortunately, I added this late. I decided I really have to address Hadoop and Spark because they get a tremendous amount of hype, and it's important to realize that they are just two more tools in the ecosystem. They're fine as far as they go. But the first thing you have to understand, and this is in the context of this presentation being about database management systems, Hadoop and Spark are not database management systems. They are massively parallel processing engines. They are ways to organize large clusters of parallel processors to solve some problems. They have data in them. They have to manage that data, but they're managing that data for the purpose of highly parallel processing. Apache Hadoop was really developed around a single algorithm called MapReduce. It can do a few more algorithms than that now, but it's basically got this architecture that's really optimized for large data sets, big data, but only in certain linear batch processing flows where it goes, the first thing it does is it splits up the data set into lots of pieces that can be processed in parallel. It processes them in parallel and it brings them back. It can therefore handle huge volumes of data, but there are long latencies to get the results. The overall speed, given the volume of data, is acceptable, but you're not going to get an answer until the very end. Also, your processing has to follow that pretty much linear model. Hadoop sits on its own distributed file system, which is a file system, not a database. There's an additional Apache product called Hive, which makes the distributed file system look like a database so you can query it with SQL. But it's fundamentally not a database. It's fundamentally a massively parallel processing system. Apache Spark, it has the same characteristic. It's for massively parallel processing. But it's better than Hadoop if you need to do iterative processing, in other words, where you're looping over the same data repeatedly, repeated queries. Machine learning algorithms definitely fall into this category, so Spark is going to be better than Hadoop if you've got a machine learning application. Apache Spark keeps its data in what are called resilient distributed data sets, or RDDs, and there's a layer called Spark SQL that makes RDDs look like a database, but again, they're really not. Resilient distributed databases are designed in order to support massively parallel processing. So I just wanted to get that out of the way because we're not going to talk about them much after this, because it turns out that Hive and Spark SQL, when you're looking at database rankings, they don't actually have a huge market share. Now, for massively parallel processing, big market share. For databases, not so much. And finally, before we get into the meat of things, I do have to point this out. If you just say, I'm going to grab some DBMS, my favorite platform, and start dumping data into it so I can process it in a big data way, and you haven't taken the time to step back and look at the data that you're going to be storing, you're going to paint yourself into corners. Because fundamentally, when it gets down to data management, to writing data and reading data, it's about the physics. How quickly can you put the data on the disks? How quickly can you index the data so that you can quickly retrieve it? And not all DBMSs are created equal. Not all data is created equal. You really have to understand the data to organize it to achieve your application's performance needs. So you really should do a data model, an entity relationship data model, or I would recommend using the concept and object modeling notation, naturally, because I invented it. And there's more detail about that on the very last slide. But you should take some thought to understanding, at least at a very fundamental level, the organization, the data, what values are keys, what values are dependent attributes, what you're going to have to index so you can reach it quickly. Otherwise, you will paint yourself into a corner. So let's look at some general DBMS features by which we will be evaluating DBMSs in general. 3 topics I'm going to cover. The first one is acid, base, and cap. Cap is a theorem about what you can compromise when you want to increase scale or speed. Second one is, what is schema on write? What is schema on read? When do you get each? And the third one, is often ignored, is licenses, proprietary licenses for database software and open source licenses, and what the issues are there. So first of all, we're talking about NoSQL, and it's one of those funny terms which is defined as a negative. NoSQL means it doesn't have SQL. It doesn't have the structured query language, the most widely used language for database management. So it's defined in terms of a negative. And it often also means no ACID, and we'll talk about what ACID means in a bit. It's a set of mechanisms that guarantee when you write data to the database, it will stay there forever. And no tables. It usually means that your data is stored as a document or it's stored as a graph, generally not tabular. But having said that, even though that's where the NoSQL DBMS movement started, it's all changing. Because what happens is, as time goes on, vendors start mimicking each other's features. And so some of the NoSQL DBMSs wanted to be able to have the same guarantee of transaction success that the traditional databases had. That's really important for financial transactions. You want to know that your deposit went into your bank balance and that it wasn't dropped on the floor by the DBMS. So some NoSQL vendors are adding ACID. Some SQL vendors are supporting non-structured data such as XML and JSON. And some NoSQL DBMSs are beginning to support SQL, like the layers on top of Spark and Hadoop that gives you SQL query capabilities. So the strong lines that used to exist between NoSQL and SQL are disappearing. This is a good thing because it gives you more options. We'll talk more about that later. So let's talk about ACID, BASE, and CAP. All three of these things are acronyms. First, ACID. This is a set of features that are part and parcel of all the traditional SQL DBMSs that still dominate the market. ACID is 4 letters. The first one, A, atomicity, all or nothing, means if you have a transaction that needs to update, let's say, 5 tables, and it's chugging along and it's updated the first 4 tables, and then for some reason it could not update the 5th table because of some kind of error. Atomicity guarantees that it will roll back all the updates, so it's as if none of the updates were applied. It's an all or nothing situation. That's a very good thing because let's say the withdrawal of money from your account succeeded, but the deposit into the other person's bank account failed. If it didn't roll back the transaction, that money would be lost to you. So atomicity is really important. Consistency says the database management system itself can enforce rules that you write, that you tell the database about to make sure the data makes sense. It's very different, by the way, from the consistency in the CAP theorem, and we'll talk about it next. Consistency in ACID means you've written some rules, the database has guaranteed them for you. Isolation means you can have multiple transactions going on at the same time, updating the same tables, and the database management system will make sure that they don't interfere with each other, that the transactions are properly sequenced so that things make sense at the end. And durability means that if the system crashes, except for the in-flight transactions, all the transactions that were already committed to the database will be there when you recover the system. These are great features. They're what we've built the data management practice on for 30 years or more. But there's a big price, and that price is scalability. You can't get to the size of a Facebook and still support ACID transactions. So sometimes one of the great contributions of the NoSQL movement to the world is you realize that sometimes it's okay to let go of these ACID guarantees in order to get scalability. So there's a fellow who wrote a theorem called CAP, which is another acronym, which is a way of saying that once you're going to relax ACID, you really have these 3 desirable characteristics, but you can only ever have 2 out of 3. It's sort of like you can't have your cake and eat it too, but this is more like cake and pie and a soft drink. You can have 2 of them, you can't have all 3. So what are these 3? Consistency. This is not the consistency of ACID. This is a different idea of consistency. Think of Facebook with its database of user posts spread across tens of thousands of computers. They all have copies of each other's data. They will not guarantee they're all in sync at the same time. If they did, that would be a guarantee of consistency. Availability says that the DBMS is going to guarantee you can always get to your data, even in the presence of the failure of some of the nodes in the processing cluster. And partition tolerance says that the DBMS will tolerate network failures where the database, which is supposed to be one thing, is partitioned into 2 or 3 chunks because you've lost some connectivity between some of the data centers. Now, you can design a NoSQL database so that it can guarantee that all the data is consistent, guarantee that it's available all the time no matter what. But if there's a network failure, the whole database is considered to be down. Or you can design the DBMS so that all the data is always available, even in the presence of network failures that partition the database, but then you give up consistency. Different partitions of the database might give back different versions of what should be the same data. Or, what's the third combination? That the DBMS can guarantee consistency, can guarantee partition tolerance, it can work in the presence of network failures, but then there will be times when it says the data is not available. So the CAP theorem says you get to choose 2 out of 3 of these things. And that leads to the CUTE acronym, which of course is the opposite of ACID, BASE. Basic availability, it's not all the data all the time, it's most of the data most of the time. Soft state, sometimes updates may be lost, and I don't know about you, but I have very clearly lost some Facebook posts from time to time. I can live with that. I don't want to lose a deposit transaction in my bank account, but I'm willing to lose a Facebook post. And eventual consistency is where the massive scale database will guarantee that eventually all of the nodes will catch up and be in the same state, but it might take a while. And so the whole realization of the NoSQL DBMS movement was that we can give up some of these traditional high-value guarantees we've had in the past in order to get giant scalability where we can afford to give them up. If we lose a few user posts, that's not the end of the world. And that enables us to have something like Facebook or Amazon's product pages or Twitter or other very large-scale applications. So we've talked about ACID, CAP, and BASE. Let's talk about schema on write and schema on read. Very simply, the traditional SQL DBMSs required that before you record any data in the database, you have to tell the database management system the shape of the data. How many tables, how many columns in each table, what are the names of the columns, what are the types in the columns. You can't write anything until you've written the schema. That's called schema on write. In schema on read, again, popularized by the NoSQL DBMSs, you just start recording your data. Usually the data then is coming in a form where the data itself has the structure, but the structure is highly variable, such as XML or JSON. You can just tell the DBMS, MongoDB, MarkLogic, whatever, create a collection of data, and I'm going to start spitting documents at you. Usually, this really started with document databases. Graph databases are the same, and search engines. You just dump the data in. And then when you read it, you have to decide what schema you're going to put your query result in, which, by the way, is really no different than what you do when you're writing a query in SQL. So SQL databases also have schema on read, but this is the lingo. Schema on read means you don't have to define any schema when you store the data. The only time you deal with schema is when you read the data. So you can't really call this a trade-off. You just have to know what you're committing to. If you commit to choosing a schema on write DBMS, you have to define your schema up front. Now, that can be a problem in the era of big data where variety is one of the 3 V's. You might not be able to define a schema up front, at least not for everything. So you might have to go to a schema on read approach. But be aware then, you have some trade-offs with schema on read, and you still need to understand the basics of your data, because no data is useful unless it has keys, unless it has values that distinguish one set of data from another. And that's why even schema on read databases have some minimal fixed schema. It might be the same schema for everything. For instance, that's how a graph database works. That's how a search engine works. There's always some schema. But that's what those buzzwords mean, schema on write and schema on read. You pay a lot of money for it, and you had to abide by those license restrictions, and they tended to be expensive. With the open source movement, that changed. Prices came down substantially. You could get access to the source code. You could often use the software without paying any fee at all. You could pay a maintenance fee if you chose to have someone help you administer the software. But you have to realize that even with free and open source software, there is a license, and it can be very restrictive. For instance, the license might actually force you to share with the world any source code you've written based on the open source software. a lot of developers, they download the free software, they start using it, they never even think about the license. And companies have ended up being liable for tens of millions of dollars in license fees because they didn't read the fine print. Now, I've read a number of licenses. They're not pleasant to read, but the reality is, as a DBMS manager, it's up to you to read the license, not up to the lawyer, because there's a lot of technology speak in there that will go right over the lawyer's head. So before you just download and use supposedly free software, you should read the license. And if you have some legal questions, consult a lawyer. There's a link on slide 17 to one of many articles you can find on the internet that make it easy to understand the most common license terms. Moving to slide 18. This is the crux of the matter. How do you choose your DBMS? You have to know what your data is. You have to know what your application needs. You have to understand what trade-offs you're making when you settle on a DBMS, because you can't have it all. You either get ACID and high guarantees of reliability but limited scale, or you choose 2 out of the 3 of consistency, availability, and partition tolerance. You give up a little of guarantees in order to get internet scales. My favorite site, and you should all write this down, db-engines.com. They've ranked over 300 databases by popularity, and they have reference data that describes every one. It's a wonderful one. And in this era of the cloud and of open source, it's very easy to try before you buy. You can just download a database, put it on your laptop, and give it a whirl. I highly recommend that after you've studied your options, if you're tending towards one database, download it, give it a try before you commit yourself or your whole company to it. So, Patrick, if you would move to slide 19, this is a snapshot of the first 10 databases that are ranked at db-engines.com, and we're going to look at many of these more closely. So moving on to slide 20, we're going to look at the first of the 5 major categories of DBMSs, and those are tabular DBMSs, meaning DBMSs that hold data in a table. Slide 21, there are really 4 styles of tabular database. There's the traditional SQL database, where everything's in tables. There's what's called NoSQL, which we'll talk about later. It's still tabular, but it's done differently. Then if you think about it, a key value database is essentially a database that allows a table to have exactly 2 columns, a key and a value. And at the other extreme, the databases, which go by a variety of names, columnar, wide column, and column family, allow you to have tables with literally hundreds of columns, and they make that efficient and they make it work. So let's look at these. Slide 22. First thing I want to identify, and I don't know if you're running this as a slideshow, Patrick, but there is animation on this slide. If you advance one, you'll see that I circled the top 4 databases: Oracle, MySQL, Microsoft SQL Server, and PostgreSQL. So what I want you to see there is that the top 4 databases out of over 300 on the market are all tabular databases. And if you look at those scores on the right, you see that they absolutely dominate the market. All the other 6 combined don't even come close. Advance one more. And by the way, I just got online and I can see what you're doing there. I'm going to let you to continue to share. The databases in position 6 and 7 are also traditional SQL databases. Advance one more, and you'll notice that the databases in positions 8 and 9, they're not traditional relational DBMSs, but they are tabular. Cassandra is a wide column store database, and you only have columns when you have tables. It's a tabular database. And Redis is a key value store, which is like having a table with 2 columns. So tabular databases are still dominating the world. Yes, they're more traditional. Yes, they're older, but they still have a huge role to play. You must not dismiss them. You have to evaluate them as possibly the right solution for your big data project. Okay, would you advance to the next slide, Patrick? Traditional SQL DBMSs, advance one more. Traditional SQL DBMSs store data in rows, although if you think about it, You know, Patrick, I'm not seeing my graphic. Can you hit advance one more time?
Oh, okay.
Yeah. If you think about it, disks are not organized in rows, right? So what does it really mean? The DBMS lays the data out in a long file, but each record in the file represents a row in a table. And you know, if you want to study that more, I've got the link there to the Oracle site where this diagram is spun from. Patrick, advance one more. What makes this work is an index. Patrick, can you advance one more slide? There we go. An index that points to where the data is in those rows. Now, there are advantages and disadvantages to this. You can get up to big data sizes with traditional DBMSs, advance, but you can't quite get to the scale of the Facebook. Advance. You can easily add additional indexes. So you design a database, you design your tables, you put it out there, you find that you need to speed up certain kinds of queries. Very easy to add indexes. But if you actually want to change the underlying table schemas, that can be very difficult. The additional indexes give you fast reads, but they slow down writes. So you can add more indexes. That's wonderful. Very easy to add indexes, but it can slow down how long it takes to do an update. These traditional DBMSs are optimal when you need to access full rows of data. But if you have data that you want to access column-wise, say you want to do a sum on just one or a couple of columns, not very efficient. Not very efficient if you've got sparse data where you have a lot of nulls. It wastes a lot of space. That's not just, the problem isn't just using up disk, but it's slower to access the data. You're spending a lot of time skipping over data that's not there. It's schema on write, which means you have to do some upfront design. But then there are a few other advantages. These databases implement ACID. You're never going to corrupt your data or have inconsistent data. And keep advancing, Patrick, for more advantages. Very well-established technology, easy to find trained people, easy to find training. The reality is almost all data languages are based on SQL, so that's, you know, a good thing. These databases have all sorts of advanced features to make data management easier. And finally, they're adding newer data types like columns that can hold entire XML and JSON documents. So lots of advantages and disadvantages. Next slide. NoSQL, I mentioned that earlier. Basically, a NoSQL database it looks a lot like a traditional SQL database, but it drops a few features, specifically ACID and joins. Now, joins are sort of fundamental to relational technologies. You lose that. You've got to do that yourself in application code, which isn't so great, but you get other advantages. NoSQL databases are built in memory so that things run very fast. They write to disk sort of as an afterthought. They're writing the cache out. VoltDB and MemSQL are two kinds of them. Now, they have advantages. The biggest advantage is they're extremely fast. That's because they don't have to go out to disk. Everything's in memory. But they're limited in size by the size of memory. Now, memory these days can get pretty big, so often that's not a limit, but in a big data application, it might be a limit. And because they're doing memory caching, ACID is not always going to be supported because they're writing the data to disk later as an afterthought. So if there's a crash, you might lose things. But everything else about a NoSQL DBMS is very similar to a traditional one, except that last one, they aren't supporting any of the newer column data types. So if you want high-speed analytical processing of tabular data, think about in-memory databases, NoSQL databases. Next slide. Patrick?
I'm on the next slide.
Oh, maybe I lost it again. Okay, key value databases. Like I say, a key value database is a database where you can have as many tables as you want, but each one has to have exactly two columns. The key is the column that's indexed, and then the value is what you find with the index. Now, again, they're making themselves more robust, and sometimes now you can index the value column. But think about it. If you could build a database and you could only index one thing in the database, that can be pretty limiting. So why do you go this way? Because next slide, very fast writes. There's at most one index or maybe two indexes that you have to update. Disadvantage is you can only do very simple querying on that one value that you've indexed, or maybe two. Another advantage, it's simple, but disadvantage for some applications, it's too simple. In fact, often when you're using key-value databases, the idea is to capture the data as quickly as possible, then put it somewhere else, a different kind of DBMS for analysis. Sometimes ACID, sometimes not. So you need to look at that. The ideal is where you can find a key-value DBMS where you can turn ACID on or off depending on what you need. And then generally, NoSQL support for key-value DBMSs. You're going to use a proprietary query language. Great. Next slide. Yes. Now, the columnar or wide column or column family DBMSs that go by several names, they are designed to support tables with hundreds of columns where many of the columns have no data in them. So they're good for sparse data. They're also good for data for column-wise access, where let's say you're doing an application and you're analyzing the closing price of a certain stock over the last 40 years, every day for the last 40 years. You really just want to look at a single column of perhaps hundreds of columns of data. Columnar makes that efficient. So for that kind of analytical application, that's the type to choose. Generally not SQL compliant and not ACID, which is okay if all you're doing is reading the data. The focus is on reading, not writing. So if you didn't get commit on your data, that's okay. Some examples are Cassandra and HBase. Yes, in Schema on write, you have to tell the DBMS what you're going to do before you write it. So those are the varieties of tabular database. Let's look at document databases. Next slide. And there are really just two flavors, JSON and XML. Now, what's the difference? Not time to go into it here, but I did write a blog at tdan.com, and there's the link. And if you get the PDF from Patrick or Elena, you'll have the link. That describes the difference. They're both called forms of document data, and they support flexible schema. Just like a human document, you can't predict what the human's going to write. With XML and JSON, the schema can be whatever you want. You still need to understand it because all data exhibits a schema, even if that schema varies, and you have to understand what the schema is if you're going to index the data so that you can get to it quickly. Some examples of these databases are MongoDB, DynamoDB, which is available at Amazon Web Services, and Couchbase. Next. So the next kind of, so some advice on document DBMSs. Ideal when your data structure is highly variable, which is very typical of textual matter that originates with humans, or if your data is coming at you at XML or JSON, or that it could be very easily converted to XML or JSON, a document database is going to serve you well. But just remember, all data has to be indexed in order to be accessed quickly. The temptation of schema on read is you just dump it in there and then you figure out how to access it later, and that can really slow you down as you realize you're going to have to reload the data because you need to add an index or you need to change the schema so it has a key. You should do some minimal modeling before you store your document data. Next, graph databases. There are two kinds of graph databases. They're very different. There are property graphs and there are semantic graphs. Next slide. So let's look at each one. A property graph is an ideal type of DBMS for doing analytical queries that need a lot of recursion, where you're writing queries that pull data and then rerun the same query on the data that just came back. The general case is friend of a friend, so that came from Facebook. Facebook wants you to know who all your friends are and who their friends are. That's a recursive query. A property graph is really good at supporting that kind of query. It also supports things like nearest neighbor, shortest path from one point to another, or page ranking, the same algorithm that Google uses to decide what the top 10 search results are when you do a query through Google. Generally, you're going to write graph data once and read it many times in order to analyze it. It's always a graph database, property graph database, it's always schema on read because the schema is actually always the same. It's a graph. And it's typically a NoSQL database. It does not need to use the SQL language. In fact, SQL is very bad at recursion, so SQL just doesn't fit the graph model at all. Depending on the vendor, you may or may not get ACID along, as a feature. Neo4j is definitely the market leader in labeled property graph databases. Next slide, we'll talk about semantic graph databases. Now, what's really interesting is this is totally different than a property graph database. Don't confuse the two. Semantic graph databases are designed to store knowledge in the form of triples, and you have a little graphic there that gives you an idea where you can have data representing people or objects or events, and then the relationships between them on the lines have meaning. Surgeon excels at operations, surgeon operated on person. And with languages like OWL, Sparkle, and Shackle, you can use this kind of database to actually have a computer compute meaning on data. It's really exciting. It can support artificial intelligence, natural language processing, and other things. And there are two examples there, GINA and Algebraics. Okay, next slide. And we'll talk about next search engines. Now, you already know what a search engine, you use it probably every day, and that's Google. Next slide. And what some enterprising companies have done is taken the Google idea of taking raw text and just indexing the heck out of it so you can find anything in the text, and allowing you to set up your own index of that data. And all of a sudden, you know, if you think about it, a database, it's basically data plus indexes. Well, a search index is like 3/4 of the database, and it can be very, very valuable. It can allow you to analyze text using queries that say, find me all the documents where you have this word and this other word within 3 words of it, so you can do natural language processing. Search engines can be very powerful, and if nothing else, you can use them as indexes into other kinds of DBMSs. Elasticsearch is one of the leading textual indexes, search engines. Solr is another one. Finally, there's a category called hybrid DBMS, and as its name indicates, it mixes the other models together, which means it doesn't force you to make a choice. You can have multiple forms of data organization without having to switch vendors, and that's a good thing. So if you advance 2 slides here, Patrick, you'll see I have a little table of database vendors that sell hybrid DBMSs and the variety of data organizations that they'll provide. And I like this because you can, if you choose one of these hybrid databases, you can have a couple of options, and if you decide, well, gee, the property graph really isn't working for us, you don't have to change vendors and change technologies just to try a different data organization. Or you might need more than one type of data organization. Why should you be forced to use different technologies? Because the data needs to be stored differently. And as time goes by, these more and more of the databases will grow up and become hybrid model databases where you don't have to change the entire DBMS just to organize your data differently. So in summary, the advice is know the different kinds of data organization that each type of DBMS supports, or perhaps forces you into, or perhaps gives you options for, as in the hybrid DBMSs. Know what it means to make trade-offs between the SQL language and non-SQL languages, between ACID and base, and you only get 2 out of 3 of consistency, availability, and partition tolerance. Model your data. Don't use schema on read as an excuse to not study your data and understand how you're going to have to set up indexes so you can get to it quickly. Study db-engines.com. It's a great resource, free resource. Before you start using anything in production, make sure you read the license. It's not as fun as writing code, but it's very, very important. Again, some companies have had tens of millions of dollars of license liabilities because they didn't read the license. They just used it in production. And finally, try before you buy. Download a trial version of something, try it on your laptop, see if it makes sense before you commit yourself or your organization. And that's all. If you can dwell on the last slide, then Patrick, we can leave that up while we have question and answer time. And I apologize for the connectivity. My connectivity came back and it's been fine, but we had that 2 or 3 minute outage. But Patrick, you did a great job advancing the slides for me. Thank you.
Thank you so much. We are going to proceed to the question. All, please post your question in the chat. And before proceeding with the question, I need to answer some of the common logistic questions coming up. Most of the questions are if we are going to provide the recording of the today's webinar. Yes, we will be providing the recording, and it will be sent to your email with which you sign up for this webinar. Also, Patrick and myself, we will be sharing with some classes which are in which NoSQL is a topic of the course. So with no more, Patrick, can you share the question in the PowerPoint?
Okay, I have one question. Just let me pull it up quickly, then I can share.
I see 2 or 3 here.
Yeah, just give me 1 minute.
I see the questions as well. I think there are 5 of them.
Okay, you can choose. Yes.
Yeah, and in fact, I think the last 4 are just logistical questions. So the top question, which is an interesting question from Jim, what is the most important thing a relational DBMS developer should know about querying a NoSQL database that is different? Well, first of all, we have to narrow the field here because many so-called NoSQL databases will allow you to query them using SQL. Hadoop and Spark definitely will, and many of the others will. So if you're ending up with a NoSQL database that doesn't support SQL, it would typically be a document database, a key value database, and a text index. I don't know if I could say there's one most important thing. If you're used to thinking about everything in tables and every table having a key, you sort of have to throw that away. Now, you still have a key in a key value database, but you only have one key. There are no compound keys. In fact, if you need a compound key in a key value database, you have to come up with some creative way of combining 3 or 4 data attributes into a single key to go in the key column of your key value database. If you're querying a graph, I suggest you take a course because thinking about data in terms of graphs is very, very different than thinking about it in terms of tables. It's a very enriching experience to understand, wow, I can ask this, I can write a query that's recursive that gets part of the graph and then recurses over that part of the graph to get another part of the graph. It's a totally different mindset. My advice is take a course. And in the case of a text database such as Elasticsearch, a search index, you'll find that those query languages are oriented towards searching text, not retrieving data from tables. And again, it's a very different mindset, very different approach to the data where you're looking for words and then other words near other words, and you're often looking for stemming, for instance. You might want to search for read, R-E-A-D, and you want to include reading and reads. Search indexes will support that. So I'm not sure I can reduce it to one important thing, but several differences. And I think that was the only queued up question.
So there are 2 other questions I just shared with you. Do you see them?
How about big table? Big table is a wide column type of database, so that's the category where big table fits. Wide column, meaning, and it doesn't mean the columns are wide, actually. It means the table is wide, many, many columns in the table, hundreds of columns in a table. And thank you for your compliments. Do I think Oracle and MySQL will continue to dominate for the next decade? Well, it's dangerous to try to predict the future 10 years from now. I don't actually think that tabular databases in general will ever be replaced. There will always be a need to efficiently handle tabular data. Think about db-engines.com that is giving you a ranking of over 300 SQL and NoSQL DBMSs. In what form is that data presented? It's presented in a table. So tabular databases are going to be around forever. Whether or not they dominate, I couldn't say, but I know there will always be major players. Now, Oracle, whether or not Oracle will dominate, Oracle has a problem because they are very expensive. And I think that as the alternatives to Oracle gain market share, it's going to nibble away at Oracle's income, and Oracle is going to not be dominant for very long. They will always have a significant market share because of the legacy effect. Just as IBM is actually still selling mainframes, the number of lines of COBOL code in production is actually going up in the world, but of course, there's a lot more activity in the non-mainframe, non-COBOL world. The same thing will happen with Oracle. They'll probably be around for 30 years, where companies will still find that it's cheaper to keep their Oracle systems going than to replace them. But I don't see them as in a position to grow much larger than they are. And was that all the questions, Patrick?
No, there are more questions. I have 3 more here.
Okay, go ahead. I can't see them.
Patrick, do you see them?
Yeah, I just saw one, and I'm sharing that right now.
Okay, I'm going to send I have several here. Because so people are sending them indistinctly to,
Oh, okay.
Yeah, I just said one. Can you see
Okay,
it?
Yes.
I said 50-plus terabytes is considered big data, so should I stick to a traditional database for my 20 terabytes of data? A very strong maybe, because at 20 terabytes, you're on the edge of what traditional databases can do. Now, there are databases such as Teradata and Greenplum, which are traditional databases, for which 20 terabytes is just well within what they're capable of doing. So you need to look at issues such as license costs, because those traditional databases tend to have much higher license costs than the newer databases. But if that data is tabular, you're probably better off with a traditional database such as a Teradata or a Greenplum that supports SQL, that can support your data. If the data is not tabular, then the issue isn't really the size. The issue is the schema is variable, and you might want to look at a document database, a JSON or XML database.
Yeah, that's the next one.
There's another question. Data
virtualization. Okay, that's a great question. Out of scope of my slides because I was talking about DBMSs, but data virtualization is a technique. It's a technology where you have this piece of middleware that can go out to a large number and large variety of data sources and make everything look like a set of SQL tables. And in many cases, the data sources are SQL tables. But what data virtualization allows you to do is avoid the work of ETL. Rather than writing code that's going to copy data from its sources into a single DBMS where you can query it, it allows you to federate the query. So you ask this piece of middleware, here's my query, and the tables I'm selecting are all over the world. The virtualization software will do one of two things. It will either fetch the data for you on demand, or it will take a piece of your query and send it to that data source, run the query there, and only fetch the results. It'll do that if the results are much smaller than the set of data you're accessing. So it does its best at allowing you to query the data where it sits rather than pulling it all into one place. And it can save a lot of work, but it won't always perform the way you'd hope. You have to, understand your data and understand if I'm querying this data that's on the other side of the continent, I'm going to incur some latencies. If it's a large query that returns a small amount of data, that's really well suited to data virtualization because it will automatically send the query to the remote site and just bring you the results. But if there's a lot of data that has to come back, then data virtualization can't optimize that network traffic for you, and there are going to be latencies. Cisco has a product that does this, and Denodo, D-E-N-O-D-O, also has a product that does this.
Those are all the questions I have. Elena, do you have more?
Yeah, there are several. They are posting them in the Q&A, not in the chat. And one is about security of big data, and the other is more concrete about the tendency of NoSQL state that in memory and cluster framework they actually can reach the ACID. Can you elaborate on this? On the possibility to? Yes.
Yes, it is possible to have a memory-based database that implements ACID. Just check with your vendor, see if they do this. The early memory-based databases did not support ACID because they used a caching approach where they would eventually write your data to the disk, and eventually meant they couldn't support ACID. But yes, it's a good point. There are some now, some memory-based DBMSs that do support ACID. The other question about security, I guess that's a generic question. These days, it's a great question. These days, you cannot consider security an option. We've all heard about Equifax. We've all heard about the many, many break-ins. You need to, if you've got sensitive data, you're obligated many times by law to protect it, and you're obligated by common sense to protect it. Ideally, you choose a DBMS that supports the encryption of data in place, so that if anybody did break into your DBMS and steal a copy, they could not make sense of the contents because it would be encrypted. The decryption only occurs when you get the query results. That's the strongest and best form of security. But there's a lot more to the security topic than that, because you have to deal with identification, authentication, and authorization. In other words, how do you know who the user is who's querying the data? How do you know whether or not they're authorized to see the data? And how do you encrypt and decrypt on the fly? Okay, next question. I see it there on the screen. If I want to build Facebook 2, do I suggest using hybrid DBMSs? For transaction, use SQL DBMS, non-transaction, use NoSQL. Yes, that is a good marriage. In other words, the example I use actually is Amazon, because Amazon, I don't know the exact number of products that they present, but it's probably over 1 million. When you think about the shopping experience on Amazon, you're doing many searches and read transactions of product data, which is sometimes in image form and textual, and there's a lot of reading and retrieving. In that context, ACID isn't very important. But when it comes time to buy, to make that purchase transaction, you want to use an ACID database, and the volume of purchase transactions is substantially less than the volume of products. So that is a good marriage where you use a NoSQL database that can scale farther, that can get bigger, because it doesn't have to be limited by the requirement to do ACID, and then you use ACID for the purchase transactions. Okay, next question. The advocates on NoSQL state that because of the in-memory and cluster framework, they actually reach ACID. Maybe.
Well, that was the question we just answered.
Oh, yeah, you just addressed that, right? Okay.
Yeah, okay. So, well, this, I hadn't read it before. This is putting a different spin on it. ACID is a very definite thing where the real thing that a vendor has to prove to say that they support ACID is if they have a crash, if the OS blows up, the hardware fails, the network fails, the disk crashes, and you lose the main the main record of the transactions, and you go through their specified recovery process. Will they recover every transaction up to but not including the in-flight transactions? If they can do that and restore their database to a consistent state, then they're supporting ACID. I think some are claiming that, well, it's so close to ACID, it's good enough for all practical purposes. Maybe, but not if you're doing financial transactions. Okay, what are some of the security challenges big data will have in the future? In my mind, the big security challenge is that developers and executives don't think about it because it's hard and it's not as much fun as writing code. You owe it to yourself, you owe it to your company, you owe it to your customers, you owe it to the world to put a lot of thought into security before you store that first byte. You have to know how you're going to protect your customers' data, your company's data, from thieves and from inadvertent disclosure. Blockchain, distributed ledger. I don't think it will replace traditional databases because the update rate of blockchain is by design very low. That's one of the things that makes it so secure. You can't just add to the blockchain without a fair amount of work to produce your next secure piece. So I don't think it'll ever replace it. Its purpose isn't really data management. Its purpose is a guaranteed ledger. That's my opinion, and who knows, I might be proven wrong eventually.
This is too new.
But I don't see it replacing.
I don't see more questions, so we had good turnaround. That was excellent presentation. Thank you again, Ted. That was quite interesting, and thank you everyone for the good question. We really had an excellent session today. And of course, as you know, this periodically we do in the ITS department, this type of webinar, and we will be continuing in this in the next semester. Thank you, everyone.
Thank you. Good night.
Thank you.
Good night.